last two columns in table 2.6.3 and 2.6.4, it is clear that the accuracy of the approximations improve as the step size h decreases. Also, we see that even though the percentage relative error is growing with each step, it does not appear to be that bad. But you should not be deceived by one example. If we simply change the coefficient of the right side of the DE in example 2 from 0.2 to 2, then at x to n equals 1.5, the percentage relative errors increase dramatically. See problem 4 in exercises 2.6. A caveat. Euler's method is just one of many different ways the solution of a differential equation can be approximated. Although attractive for its simplicity, Euler's method is seldom used in serious calculations. We have introduced this topic simply to give you a first taste of numerical methods. We will go into greater detail and discuss methods that give significantly greater accuracy, notably the fourth order Runge-Kutta method in Chapter 6. We shall refer to this important numerical method as the RK4 method. Numerical solvers. Regardless of whether we can actually find an explicit or implicit solution, if a solution of a differential equation exists, it represents a smooth curve in the Cartesian plane. The basic idea behind any numerical method for ordinary differential equations is to somehow approximate the y values of a solution for pre-selected values of x. We start at a specified initial point, x to the 0, y to the 0, on a solution curve and proceed to calculate in a step-by-step fashion a sequence of points x1, y1, x2, y2, xn, yn, whose y coordinates yi approximate the y coordinates yxi of points x1, yx1, x2, yx2, xn, yxn. That lie in the graph of the usually unknown solution yx. By taking the x coordinates close together, that is for small values of h, and by joining the points x1, y1, x2, y2, xn, yn, with short line segments, we obtain a polygonal curve that appears smooth, and whose qualitative characteristics we hope are close to those of an actual solution curve. Drawing curves is something well suited to a computer program written to either implement a numerical method or to render a visual representation of an approximate solution curve fitting the numerical data produced by this method is referred to as a numerical solver. There are many different numerical solvers commercially available, either embedded in a larger software package such as a computer algebra system or as a standalone package. Some software packages simply plot the generated numerical approximations, whereas others generate both hard numerical data as well as the corresponding approximate or numerical solution curves. As an illustration of the connecting the dots nature of the graphs produced by a numerical solver, the two red polygonal graphs in figure 2.6.3 are numerical solution curves for the initial value problem y equals 0.2xy, y0 equals 1 on the interval 0, 4, obtained from Euler's method in the RK4 method using the step size h equals 1. The blue smooth curve is the graph of the exact solution y equals e 0.1x squared of the IVP. Notice in figure 2.6.3 that even with the ridiculously large step size of h equals 1, the RK4 method produces the more believable solution curve. The numerical solution curve obtained from the RK4 method is indistinguishable from the actual solution curve on the interval 0, 4 when a more typical step size of h equals 0.1 is used. Using a numerical solver, knowledge of various numerical methods is not necessary in order to use a numerical solver. A solver usually requires that the differential equation be expressed in normal form dy divided by dx equals fxy. Numerical solvers that generate only curves usually require that you supply f, x, y, and the initial data x0 and y0 and specify the desired numerical method. If the idea is to approximate the numerical value of ya, then a solver may additionally require that you state a value for h, or equivalently, require the number of steps that you want to take to get from x equals x0 to x equals a. For example, if we want to approximate y4 for the IVP illustrated in figure 2.6.3, then starting at x equals 0, it takes 4 steps to reach 8x equals 4 with the step size of h equals 1. 40 steps is equivalent to a step size of h equals 0.1, although it is not our intention here to delve into the many problems that one can encounter when attempting to approximate mathematical quantities. You should be at least aware of the fact that a numerical solver may break down near certain points or give an incomplete or misleading picture when applied to some first-order differential equations in the normal form. Figure 2.6.4 illustrates a numerical solution curve obtained by applying Euler's method to a certain first-order initial value problem. dy divided by dx equals fx y, y0 equals 1. Equivalent results were obtained using 3 different commercial numerical solvers, yet the graph is hardly a plausible solution curve. Why? There are several avenues of recourse when a numerical solver has difficulties. 3 of the more obvious are decrease the step size, use another numerical method, or try a different numerical solver. A numerical method. Page 73. The end.